Okay, welcome to the ACEMS virtual public lecture for today, Uncertain Futures. What can we forecast and when should we give up? Before proceeding, I want to acknowledge the traditional owners of the land on which I live and currently work, the Wurundjeri people of the Kulin Nation, who've been custodians of this land for thousands of years. I pay my respects to their elders past and present, and to Indigenous communities who may be online today. Now, please note that this lecture will be recorded and made available on the ACEMS website. It's www.acems.org.au. And for those of you unfamiliar with ACEMS, ACEMS is the Australian Research Council Centre of Excellence for Mathematical and Statistical Frontiers. My name is Tim Garoni. I'm a Chief Investigator with ACEMS and the Deputy Director responsible for outreach. And I'm very pleased to be able to introduce Rob Hyndman as today's speaker. Professor Hyndman is the head of the Department of Econometrics and Business Statistics at Monash University, and he's an ACEMS Chief Investigator. From 2005 to 2018, Rob was Editor-in-Chief of the International Journal of Forecasting and a Director of the International Institute of Forecasters. Rob's the author of over 200 research papers and 5 books in statistical science. He's an elected fellow of both the Australian Academy of Science and the Academy of Social Sciences in Australia. In 2007, he received the Moran Medal from the Australian Academy of Science for his contributions to statistical research, especially in the area of statistical forecasting. And Rob was also recently the recipient of the 2021 Pittman Medal from the Statistical Society of Australia. For over 30 years, Rob has maintained an active consulting practice, assisting hundreds of companies and organizations around the world. He's won a number of awards for his research, teaching, consulting, and graduate supervision. At the end of Rob's presentation, we will be taking questions. Please use the Q&A button at the bottom of your screen to post questions. And without further ado, I'd like to invite Rob to speak to us about uncertain futures.
Thank you, Tim. Thank you for the introduction, and it's great to be with ACEMS in this public lecture. So I'm going to talk about some of my work in forecasting over the last maybe about 30 years, and hopefully draw some lessons generally about forecasting and what we can do as statisticians in this field. So let me just start by talking about what people have tried to forecast and where things have gone badly wrong in the past. Going way back to the 1940s, the chairman of IBM said, I think there is a world market for maybe 5 computers, which was a disastrously wrong forecast, which fortunately they corrected before the company went bust. In 1977, another head of a big American tech company said there's no reason anyone would want a computer in their home. The date's interesting. 1977 was 3 years before the first PC was produced by IBM. DEC no longer exists. A bad forecast that led to the demise of the company eventually. And coming to more recent times, we're all familiar with the forecast of Donald Trump, who said we're going to be opening relatively soon. The virus will go away in April. He said that in February 2020. And even closer to home, our own Prime Minister said we expect that Australians will be fully vaccinated by the end of October. He said that at the end of December 2020. So there's a long history of people in power making very bad forecasts and bad decisions as a result of those forecasts, which clearly shows that forecasting is important, but maybe is a little difficult. Another thing I want to say before I get into my own forecasting experience is that sometimes people call things forecasts when they're clearly not really forecasts. So here's an example from Treasury documents, Australian Treasury documents, which usually provide what they call forecasts of the underlying cash balance as a percentage of GDP. And if you look at these forecasts over the years between 2011 and 2017 and compare them with what actually occurred, it's pretty clear that they weren't trying to forecast the actual underlying cash balance because they're all extremely optimistic. And a forecast by definition is somewhere around the middle of the likely values that could occur. And so you would expect about half the time to be underestimating and about half the time to be overestimating the actual value. So when you get a situation like this, it's pretty clear that they're not trying to forecast in that sense, in the statistical sense. I call these hopecasts rather than forecasts. This is where an organisation or somebody's been asked to produce something that tells a story rather than represents the most likely outcomes in the future. So it's always worth remembering that sometimes people call things forecasts when they're not forecasts. So when I tell people I do forecasting, there's usually one of two reactions. The first most likely one is, oh, you're one of those people that forecast the weather, are you? Because apparently when people think forecasting, they only think about the weather. Well, I don't do any weather forecasting or climate forecasting, so that's not what I do. The other most common reaction is, oh, you're one of the people that forecast the stock market. And no, I don't do that either. I almost never do any work on financial forecasting, but some people do. And that's also an interesting area, but I'm not one I'm going to say much about. A closely related topic is forecasting exchange rates. And if you could do that accurately, then you could make a lot of money. And one of the things I tell my undergraduate class when I teach forecasting is that forecasting something like a stock price or an exchange rate, you're really only going to do much better than everyone else if, and therefore make money, is if you have information that other people don't have. And many times that's illegal, having information in advance or insider information about what's going on. Unfortunately, one of my students took my comments to heart and has since spent some time in prison from using insider information for forecasting the exchange rate. So what do I actually forecast? If I'm not forecasting the weather and I'm not forecasting stock markets or exchange rates, let me tell you about a few things that I have forecasted. So I'm going to give 4 sort of small examples or case studies in this talk to illustrate some of the sort of things I do. So the first of them is forecasting pharmaceutical sales. The Australian government subsidises pharmaceutical sales, and therefore we need good forecasts of the sales so that the government can plan their budget. I have done quite a bit of work on forecasting electricity demand for all states in Australia, and I'll talk a little bit about that. Currently, one of the things that I'm interested in is trying to forecast COVID-19 cases, and I'm doing that for all of the state governments and the national government of Australia. And another thing I've done relatively recently is attempt to forecast when the tourism in Australia will recover from the pandemic. And I'll talk a little bit about that work as well. Okay, but before I talk about those 4 things, let me just get you to think a little bit about forecasting and what makes something hard or easy to forecast. So I've got here a list of 8 things, and I'd like you to think about which of these is the easiest thing to forecast and which of them is the most difficult. And they range from things in a very short period ahead, like tomorrow, to things in a few days' time or a week time or a year's time or many years' time. So which of these is the easiest one to forecast and which is the most difficult, and how would you put them in some kind of order? So we haven't got time to do that as a group exercise, and it's a little difficult doing it as a virtual group exercise with hundreds of people simultaneously. So here I've done it. Here's my answer to that question. And in my classes, we do this as a group activity and then we discuss the results. So my answer to this is that of those 8 things, the easiest one to forecast is the time of sunrise this day next year, which, although it's a long way away, we can forecast extremely accurately. So accurately, in fact, that people don't often think of that as a forecast. And the timing of the next Halley's Comet appearance is also something we can forecast very accurately, even though it's many decades away. the reason we can forecast those accurately, I'll come to soon. Then I would put things like temperatures in the very short term. Temperature tomorrow is relatively straightforward to forecast. Electricity demand in a few days' time. Sales of drugs in Australian pharmacies. And then we get to the difficult ones, the stock prices and the exchange rates, which are roughly equally easy to forecast for the same time period, but I'll put them in order of the time period. So the one tomorrow, one next week, and one in 6 months' time. In doing that exercise, you immediately start thinking about, well, what do you mean by easiest here? How do you measure easiest? And I'll come to try to answer that question towards the end. And another thing that comes up is what makes something easy or difficult to forecast? Why did I put them in this order? Why do I, and intuitively you might think, well, yeah, sunrise is easy to forecast relative to stock prices, but what makes it easy? What is it about sunrises that makes that an easy problem? So I've thought about this for a while, and I've been asked in quite a number of media interviews, what is it that causes this ordering to occur? And I've come up with some 4 things. The first is something is easier to forecast if you have a good understanding of the factors that contribute to it and can measure them. So if you know what's causing it. Secondly, you need to have a lot of data. Thirdly, you want the future to be similar to the past in a way that you can model. And fourthly, you don't want the forecast affecting the thing you're trying to forecast. As soon as the forecast can affect the thing you're trying to forecast, then that becomes a much more difficult problem. So if you think about these 4 factors in terms of the things that we looked at before, you can see why sunrises are easy and stock prices are difficult. Sunrises are easy because we have an extremely good understanding of of the astronomy that goes into that. There's lots of data. The future is pretty much identical to the past, and there's no way our sunrise predictions can affect what the sun is doing. Whereas with stock prices, we don't have a particularly good understanding of what's causing those fluctuations, and the financial news every night on TV is a sort of a post hoc justification for some of those fluctuations. But sometimes I think it's more commentary about noise than actually understanding the causal factors. There is a lot of data available, and usually the future is similar to the past, although occasionally things happen. We have financial crises or major events happen that change the nature of the price we're trying to forecast. And crucially, the forecasts do affect the thing you're trying to forecast. If someone's well known, if someone like Warren Buffett, for example, says something about a stock price, that will affect the price of that stock. So your forecast will affect the thing you're trying to forecast if you are sufficiently well known. Okay, so that's sort of the background. And now I'm going to talk a little bit about what I mean by a forecast, really. I've sort of done it vaguely, but let's try to be a bit more explicit and rigorous about what we mean by a forecast here. So here's my definition, that a forecast is an estimate of the probability distribution of a variable to be observed in the future. So it's about something that occurs in the future. It's probabilistic. You're trying to understand the uncertainty of the thing you're trying to forecast. And of course, we don't know that, so we're estimating it. So let me give you an example if that's not clear. So here's a series of observations of the number of short-term visitors to Australia every month over about 18 years. So from 2000 until the end of 2018. And you can see that there's an increasing trend and there's some quite strong seasonality. This pattern occurs every year. So what we do when we forecast is we fit a model to that, and we think about what that model says about how the future is likely to unfold. And so we can generate future possibilities. So here's an example. This is a simulated future from a model fitted to the data in black. So that's one way the future might unfold with this particular series and this model. If I run the model again, I can get a different future. And I can keep doing this, and I can build up an idea of what the distribution of possible futures might look like. And if I do it enough times, I get quite a good understanding of the space that the futures could lie in, where it's unlikely to be down here and it's unlikely to be up here, but it's the whole space of possible futures can be then, you can think about it as a probability distribution. So if I now take all of those futures, thousands of them, and I can look at where the middle 50% lie and where the middle 90% lie, and I get an idea of the range that are most likely to occur. So let's just zoom in on that section of the graph, and you can see that the solid blue line is the average of what's going to happen in the future. So we don't think the blue line is what's going to happen. It's the average of all of the things that could happen. The darker blue region is where the middle 50% of possibilities lie, and the lighter blue region is where the middle 90% of possibilities lie. So there's a 10% chance is going to be outside the light blue region. And you can see that some of those simulated futures shown in grey lie outside that. So when I think about forecasting, that's what I'm doing, is I'm trying to estimate a probability distribution for each possible future time period. Then, of course, you can look and see what actually happened to see whether our forecasts were any good. So here I'm forecasting short-term visitors to Australia, and I can take what happened since January 2018 and have a look at how well we did. And you can see that for the first 2 years, those forecasts are actually pretty good. About 50% of the actual values lie inside the 50% shaded region. About 90% of the actual values lie inside the 90% shaded region until January 2020. And then after that, the pandemic had an effect. And of course, our forecasts are now completely wrong. The reason is that the future is not similar to the past. And so while the future was similar to the past up until the end of 2019, our model was great. Since around February 2020, our model has not done very well at all here. Okay, so that's sort of what I'm trying to do when I'm doing forecasting. I'm trying to estimate those probability distributions. So I now want to do 4 case studies. These are from my own consulting practice. I'm going to show you some of what we did and what we might have learned from them. In each case, I'm not the only person doing this. There's at least one other person and often a whole team of people involved. And I won't always say everyone else is involved, but just wanted to point out that this is all joint work. So firstly, let me talk about forecasting the pharmaceutical benefits scheme. So that's the Australian government drug subsidy scheme. When you go to the pharmacy and you buy some kind of prescription drugs that are on this scheme, then you don't pay the full price. You pay some of the money and the government will pay the pharmacy the rest of the money. Of course, the government doesn't know who's going to get sick, who's going to need different prescription drugs, so they have to forecast the number and types of drugs purchased so that they can put the money aside in the budget. It's a lot of money. It's about 1% of GDP. It's been about 1% of GDP for most of the last 20 years. And the total cost is budgeted on forecasts. So I got involved with this problem about 20 years ago when this was what the ABC website looked like. And this was one of the articles on that website. It shows you how bad the websites looked in those days, but it also demonstrates what the issue was. You can see here the articles calling for tighter controls, or the opposition was calling for tighter controls on drug prices after the budget had blown out by about $800 million. And this was the second year in a row that had happened, that it had blown out by more than $500 million, which is a lot of money, even for a government to find. And so I had a phone call eventually to say, could I help with this problem? So the phone call went something like this. I'm sure you understand that there's been a problem with our forecasts of the PBS. So I asked them questions about it. They had underestimated a $4.5 billion budget by about $800 million. So that's a huge percentage. Not good. There were thousands of products. The products were highly seasonal. So you need to forecast the sales of all of these different products. The products are subject to all sorts of fluctuations and volatility. Sometimes it's covert marketing by the drug companies. Sometimes it's drugs coming on and off the PBS at different times. So a drug might be on for a while and then it might come off and then it might go back on, or a new drug might be developed that suddenly comes on and causes a lot of sales. I asked them about the available data. They said they had monthly data available for 10 years, which sounds great. Like that's a lot of data for thousands of products. It's what you love as a statistician, to have plenty of good data. But then they told me that they weren't sure how to deal with the seasonality, so they aggregated to annual values. Okay, so we're now down to about 10 observations per product. And then they told me they didn't trust the reliability of the data, and so they were only using the first 3 years of the data when you estimating the forecast. So the first 3 years, that means the data is 7 years old at the time they're producing forecasts, and only 3 observations. And I said, what are you doing with the 3 observations? And they said they're using the forecast function in Microsoft Excel, which fits a straight line through those 3 numbers. So I assured them that I could help, because whatever I did was going to be better than that. Let me show you some of the data and also some of the forecasts. So this was much later, obviously. So this is showing data only from around 2000 through to around 2007. It's more recent data than the problem that they rang me about, because I've been involved with the problem since then. So this is one group of products, and you can see that there's a trend, not much seasonality, and our forecasts sort of look reasonably good. Here's another product. There's a trend, there's quite strong seasonality, there's increasing seasonality and increasing fluctuations. You see the size of these ups and downs gets bigger, and our model does really well in forecasting that. Here's one where there's been a period where there was a sudden drop in expenditure and then an increase, probably because drugs came off the PBS and then went back on. Because of these wild fluctuations, our forecast intervals are very wide in this case. In fact, they go negative, which makes no sense at all. So these are not good forecasts. Here's one where there's been a sudden jump, probably because a new drug came on the market, and our forecasts haven't done very well because they haven't adapted to the changed pattern. So the pattern's quite steady up until about 2007. The change in seasonality and the change in level has caused our model to get a bit confused. So that's the sort of thing that we do with PBS. I've shown you a couple of cases where we did really well and a couple of cases where it didn't do very well. I had to pick those out because most of the time it actually does really well. And as a result of this project, we developed an automatic forecasting algorithm for a type of model called an exponential smoothing state space model. And it was the first time a fully automatic algorithm had been developed for these types of models. It allowed for time-changing trend and time-changing seasonal patterns. It usually took a couple of years if it changed dramatically before the model adjusted, but it was adaptive to the different methods. And the most important thing is that the forecast mean absolute percentage error, so MAPE stands for mean absolute percentage error, it reduced from nearly 20% down to about 0.6%. So a huge reduction in forecast error, which means that the budget, instead of being out by, between $500 and $1 billion, was now out by about between $50 and $100 million, which is a much more reasonable amount of money to have to find if necessary. The state space models provided prediction intervals, and as a result of this project, we then started writing papers about it, and the theory and algorithm was first published in a paper in 2002, and it's gone on to be probably the most widely used forecasting algorithm in the world. It's now implemented in lots of software, including my own packages, the ETS function in the forecast package and the uppercase ETS function in the Fable package, but also in other commercial products such as Tableau and SAS and elsewhere. You've made it when Microsoft Excel tries to implement something you've done but fails badly. So they put out a function a few years ago called the forecast.ets function, which you would think implemented the ETS modeling framework that we developed in this project, but actually it does something different and badly and should not ever be used. But that's typical of Excel. Okay, so let's go back to those 4 factors and think about, well, how did they fit into this problem? We have a reasonably good understanding of the factors that contribute to drug sales. We know about the seasonality. We know about drugs coming on and off the market. We know about changes of government policy. So we have a pretty good understanding of what's going on. There's a fair bit of data available. The future, as though, is not that similar to the past at times, because new drugs get developed that might be a game changer for certain conditions. And that was what was happening back in 2001. There was 2 drugs really that had come on the market that had changed the nature of treatment for 2 quite common conditions, and the models hadn't allowed for that. But so that's somewhat of a problem. But the forecasts don't affect the thing you're trying to forecast. Our forecast of the PBS expenditure will not change the way people go and spend money on pharmacy products. So mostly these are satisfied, which is what makes it a relatively easy problem to forecast. Okay, let me do a second example. I'm going to talk about peak electricity demand now. So that's where you want to forecast the amount of power that people use. So this is statewide, and again, like most of these problems, it began with a phone call. This was now 2006, and I had a phone call from someone at the South Australian Energy Market Operator, which no longer exists. We now have an Australian Energy Market Operator, but back then there were state-based operators. And a person from South Australia rang and said, we're interested in forecasting the peak electricity demand in a half-hour period in 20 years' time. Sounds like a horrendously difficult problem. He did have a lot of data he could provide me. They had 15 years of half-hourly electricity data, half-hourly temperature data at various weather stations across South Australia, and economic and demographic data at quite high quality because they're collected by the Australian Bureau of Statistics. South Australia is an interesting place to do this because I was told it's the most volatile electricity demand in the world. So this sounds like an impossible problem. However, based on those 4 principles, or the 4 conditions for what makes something hard or easy to forecast, this should be a relatively easy problem because we know the factors that are driving it. There's lots of data. Your forecasts don't affect the thing you're trying to forecast. And the future is, at least in the short term, up to a few years ahead, pretty similar to the past. Once you forecast about 10 to 20 years ahead, technology could change so much that the future might be very different from the past. But at least in the short term, it looks like a relatively straightforward problem. So I should say that the 20 years ahead, that's pipe dream. You can't do that because the changing nature of electricity usage could be extremely different in 20 years' time with electric cars, for example. But in the short term, it's not too bad. Let me show you what the data looks like. So this is statewide demand data for Victoria. So it's a later data set and a different jurisdiction. But it gives you an idea what the problem looks like. So you can see there's a winter peak, which is these lumps here. There's summer peaks, which are much more volatile and much more skewed, and are largely driven by weather. Let me just zoom in on a summer period. And you can see here for Victoria in the summer of 2013, 2014, you can see a little bit more detail about the patterns. You get these periods of hot weather, which is causing these peaks here and here. You get periods of cooler weather, so you get demand a bit lower. There's a weekly pattern, which you can see easily here. That's a weekend, and there's another weekend. You can see it here and here. And you get public holiday effects. And a time of day effect, which is the smaller fluctuations up and down every day. You can see that it's driven by temperatures just by plotting demand and temperature on top of each other like that. So when the temperature's up, the demand is up. And these peaks coincide pretty closely. If I plot demand against temperature, you can see that there's a heating effect in this direction and a cooling effect in this direction. And in fact, if I split it by non-work days and work days, you can see that the non-work days have lower demand generally than the work days. And I'm going to split it up again this time by time of day. So let's now split into half-hourly periods. And I'm just going to run time forward every half-hour period from midnight. And you can see in the middle of the night, there's not much difference between work days and non-work days, and there's not much temperature effect. And as the day continues, the work days and non-work days separate more, and the temperature effect gets stronger, particularly the heating effect in the earlier part of the day and the cooling effect in the later part of the day. And if I split this again by time of year, you'd get, of course, different effects. You'd get more of the heating effect in winter and the cooling effect in summer. But you can see that there's quite a complex relationship here between the time of day, what type of day it is, and the nature of the temperature. And it's a non-linear relationship that with interactions happening between each of these different contributing factors. So to build a model of this data, we're going to have to build quite a sophisticated model that allows for all of this behavior to occur. And the peak demand, which is the thing that the organization was interested in at the time, is occurring in late afternoon. So you can see this is 2 p.m, it's getting up there, and around 4 to 5 p.m. is where the peaks are occurring, just here. And then after 5 p.m, it'll drop off again like that. So the predictors here are calendar effects: time of day, day of week, time of year, and holidays. The prevailing and recent weather conditions. It's not just what the current temperature is, it's also what the recent temperatures have been because of thermal inertia in buildings. And of course, for long range forecasting, we have to think about climate change. Electricity companies are introducing incentives for people not to use power at certain times of the day. That's called demand response incentives. Changing technology, more efficient air conditioners, for example, will change the patterns. And of course, economic and demographic changes have an effect. So it's a complicated model that builds all of these things together. But we do have a pretty good understanding of the factors. There's a lot of data. The future is similar to the past in the short term, but not the long term. And the forecasts can have some feedback, because if we forecast a lot of demand, the energy companies may change the price, which will affect the demand for some customers. Residential customers tend not to have these differential prices, but industrial and business customers do. So the 3 and 4 are not entirely satisfied, which makes it a somewhat more difficult problem. Okay, let me now come to something more recent, which is tourism forecasting post-pandemic. So this is a problem that my co-author Georgia Thanasopoulos and I were approached by Tourism Australia, and they, in the end of 2019, the date's important, it was the end of 2019, and they said, could you help us forecast tourism numbers for the next few years? Before the pandemic was a thing, before we knew anything about it. And we said, yep, that sounds like an interesting project. George is an expert on tourism modeling, and together we worked on the forecasting of this. About 6 weeks into the project, we realized that, you know, our forecasting approach was not going to work because of the pandemic, and we had to change tack, and we did, and we introduced and developed new methodology to try to forecast what would happen as a result of the pandemic. So this is a graph from our report, and you can see here the arrival numbers. This is quarterly data from 2005 through to the end of 2019. So this is arrival numbers. You can see it's increasing. There's seasonality because people come to Australia at some quarters more than others because of, it's a better place to holiday at some times of the year. And you can see our forecast here, which is based on a large survey of forecasting professionals and experts and stakeholders. And we asked them to give us optimistic, pessimistic, and most likely forecast. And then we came up with a mixture. First of all, we came up with a way of turning their expert judgment into probability distributions, and then created a mixture distribution, which is the one in pink here, which is our best estimate of what was likely to happen. And this was done early 2020. And of course, now we're sitting here in 2021, and the pessimistic forecasts were actually much closer to the truth. In this case, we don't have a particularly good understanding of the factors contributing to it because we don't know about how people will react to traveling post-pandemic, and we don't know how the economy is going to respond. There's almost no data available in a post-pandemic world about tourism. The future is very different from the past, but the forecasts don't affect the thing you're really trying to forecast. So most of these factors are we don't have these conditions which enables easy forecasting to occur. Let me now go to my fourth example before trying to sort of sum up some of the lessons we've learned. And this one is the one that I'm most actively involved with right now. In fact, this morning, I had a meeting with the COVID forecasting team, and we meet every Tuesday morning and have done since March 2020 to discuss forecasting COVID-19 cases for all states in Australia. So we actually report to the Australian Health Protection Principal Committee. It's a key decision-making committee for national health emergencies. It's been around for a long time. It wasn't just formulated for this particular emergency, but it's a long-standing committee that comprises all state and territory chief health officers. It's chaired by the Australian Chief Medical Officer, and it provides advice to the state governments and the national government. There's a lot of people involved in this project from many organisations, including the Doherty Institute, the University of Melbourne, the University of Adelaide, Curtin University, and Monash University, and a few from elsewhere as well. Most of the people involved are listed on the screen, but it's a moving thing. People come in and out of this group. So I may have missed a few people off. So what do? We get case level data of all positive COVID-19 tests, both the onset time and the detection time. So that's now many thousands of cases. We get daily population mobility data from the tech companies such as Google, Apple, and Facebook, which tells us how much people are staying home, how many people are in workplaces or in shopping centres or in parks and gardens and so on. So we can see how people move around, which helps us assess whether they are following various restrictions introduced by the state governments. We also get results from contact surveys every week, weekly non-household contact surveys, how much you interact with people outside your house, and other behavioural surveys to try to measure how well people are following the rules. And we have case numbers from lots and lots of countries and regions via the Johns Hopkins University COVID-19 repository. And from these different data sources, we build three different models. Before I get to the models, let me just show you what the data looks like. This is the data as of today. So the data plotted as the number of daily cases by date of symptom onset. So it's not the same as the reported numbers that you see in the media. It's the numbers by the date that the first symptoms occurred. So the numbers don't look what you might think they will look like. The number of 700 cases per day was reported in Victoria back in August 2020, but actually by date of symptom onset, it was the highest was only in the 400s. This is the current New South Wales outbreak, which is now it has been quite concerning for a long time. The recent numbers are relatively uncertain and incomplete because we don't know the date of onset until symptoms show and a test is obtained. So what we do is we build three models. There's a epidemiological model called an SEIR model, which is largely developed out of the University of Melbourne and the Doherty Institute. There's a sort of agent-based or microsimulation model, which we call a generative model, which is largely developed at the University of Adelaide. And both of these have inputs from Curtin University. And then there's a model that we've developed in my group at Monash, which is a global autoregressive model. So it's a time series model. So it only uses the time series data, not the rest of the data, but it uses it for all countries and regions. So there's a lot of data goes into it. And we remove countries with obvious anomalies like negative cases and strange things that go on. And so those three models then generate forecast distributions, and we combine them in an equally weighted mixture, also known as linear pooling. So we combine these three things, and that is the forecast that goes to the governments. This combination approach helps us to take into account the fact that none of the models are perfect, but hopefully they all capture something a little bit different about what's going on. And generally it's known that this approach using an ensemble works best when models tend to be a little overconfident and they use different data sources, and we're pretty sure that's happening here. Just show you some of the examples of the forecasts that we produce. So here's, this was in the middle of September last year in Victoria. And you can see we show the dark blue line is the median of the possible future samples. Then the prediction intervals shown are 50%, 60, 70, 80, and 90% intervals. So you would expect 10% of cases to not lie in any of these intervals, and about half of them to lie in the darker blue region here. The actuals are shown in black. So I point out that the models that produce the prediction intervals are based on a lot more data than the what is shown on the screen. This is just the historical data for the thing we're trying to forecast, but the inputs to the model are much more rich than that. Here's another example. So this was towards the end of last year when we had a long period of 0 cases, and our models were showing that it was still possible to take off. And in fact, it did take off during that period, the 4-week period that we forecast. Here's an example where our model didn't do very well. We had a long period of zeros in March and April, then a single case towards the end of April, and our model was showing, you know, possibility of a major outbreak was quite low, but in fact it took off to some extent towards the end of May, outside our prediction intervals. And here's a more recent one. This was predicting in the end of June and July. So we do this every single week. And have done now for nearly 18 or more than 18 months. So how easy is this to do? Well, we have a very good understanding of the factors that contribute. We know about the disease transmission. We know about the distancing and how that affects disease transmission. There's now plenty of data, although there wasn't back in March 2020 when we started this, and we were having to sort of make a lot more assumptions. Now that we have a lot more data from a lot of countries and we have a better understanding of the transmission, that particular condition is now, we're pretty good on that. The future is not similar to the past because of changing variants. So the Delta variant meant we had to change a lot of the parameters in our models. Vaccinations have meant we're changing again. And as vaccination numbers increase, the future is different from the past. And so we're having to allow for that. And the forecasts directly affect the thing you're trying to forecast, because that's the whole point of these forecasts. They go to the National Committee and the AHPPC committee that I mentioned earlier. They also go to the National Cabinet, and decisions are made on the basis of these forecasts to change conditions, which makes, of course, the forecast then wrong, because the conditions under which they were produced would no longer be relevant in the future. So this is a very challenging problem to try to solve because of these factors. Okay, let me just now say a little bit about how you decide if your forecasts are any good. So as I've done in this presentation, it's all about the distribution. It's not about forecasting one number. If it was just about a single number, then evaluation is just saying, well, how close is what I predicted to what actually happened? And you just take the difference, for example, between what you predicted and what happened, and that gives you a score, which says how well you predicted. So if we were just predicting the median, for example, then you would just look at the median and look at what actually happened, and the difference would tell you how good your forecast was. But we're not just predicting the median, we're predicting the entire probability distribution. And every point on this axis is possible with different probabilities. The most likely outcomes are actually back here where the probability is highest. The least likely are out here or down here. And our forecasts include, the whole thing. So the 90% percentile, or the 0.9 quantile, means that there's a 10% chance of it being bigger than that, a 90% chance of it being lower. So we have to ask the question, well, how good is our 0.9 quantile when all you get to see is one outcome? So we're assessing the entire probability distribution on a single outcome, the actual value. So that's a hard problem. So I'll explain how it happens. Let's suppose we're just interested in the 0.9 quantile. Well, you can score it based on where the actual occurred. You would expect the actual to occur to the left of that because 90% of the time it does, and only 10% of the time it should occur to the right of that. So if the actual occurs to the right, we're going to score it high. The further away, the higher it is. So if our actual was out here somewhere at 10, we're going to get a score which is a high number. If our actual is down here on the left-hand side, which is where you expect it to be, we're going to score it low. A low score is good, a high score is bad. So our actual was here, so the score is going to be a pretty small number because that's about where you would expect to see it. We do the same for every other quantile. So the 0.7 quantile, it looks like that. The 0.5 quantile, you expect half the time to be on the right of that and half the time to be on the left. So the scoring is symmetric. The 0.3 quantile and the 0.1 quantile, you expect it mostly to be on the right-hand side of that and not very often on the left. And so you score it high if it's on the left and low if it's on the right. So you do this for every possible outcome from 0 all the way up to 10. So let me just show you, let me just show you how that works. So as we run across the entire range of possibilities, for every one of those quantiles, we get a score, and I'm plotting those scores on the left-hand side. So for every possible outcome across here, we get, I know the probability of it being to the left of that, which is what I've got on the horizontal axis, and the score is how good my forecast was, which has got what I've got on the vertical axis. So we turn this one single number into a graph like this, which tells me how good the forecast was for that particular possibility. And then the area under that graph is called the continuous rank probability score. So it's the value, it's the score which tells me how good my forecast was. So you do that for every possible thing you're forecasting. So for all of these distributions, we get a CRPS value, and we can average them across all of the different distributions to know whether our models are doing very well. So if I do that for the 3 COVID models and the ensemble, I can get a graph like this. So now I'm plotting the average CRPS on the vertical axis against how far ahead I'm forecasting on the horizontal axis. And I'm averaging it over all the forecasts we produced between September and June, September last year and June this year. And you can see that some models do really well. So the SEIR model did really well in Victoria, whereas the generative model didn't do quite so well in Victoria. But in Queensland, the SEIR model is doing pretty badly, at least for long-term forecasts, although all the models are doing quite well for the shorter term. The SEIR model is also doing badly for South Australia, but doing really well for short-term in New South Wales. So the different models do better, some in different states, some at different horizons. The ensemble puts them together, that's the line in orange, and it's always sort of reasonable. It's not necessarily the best, although it sometimes is, as it is here in New South Wales for the longer term, but it's always not too bad. And so that's the model that goes to the government, and that's how we know that it's a reasonable forecast, because we compare it using these CRPS values. Let me finish by going to the second question in my title. So the first question is, what can we forecast? And I've shown you some of the things we can forecast. The second question is, when should we give up? So should you give up if there's insufficient data? Well, we've seen an example when we had no data really with the forecasting the tourism numbers post-pandemic. And I argue that still our forecasts were useful because that gives the government some idea of the range of possibilities that could occur and how likely each of those is to occur. So even though the prediction intervals were enormous and our forecasts were saying this is an extremely uncertain environment, that in itself is useful information to know that it's uncertain. Otherwise, if you're overconfident about what the future might hold, you will make bad decisions. Knowing that it's highly uncertain and that your forecast prediction intervals are enormously wide is actually useful to know in making decisions. What about when the models give implausible forecasts? We saw a couple of examples of that. That just means the model needs to be fixed. Find a better model that gives better forecasts. So no, I don't think that should be when you give up. That should be when you double down and figure out what's gone wrong and what assumptions have you made that are not relevant, and how can you improve the forecasts. And when the forecast uncertainty is too large to assist decision making, I don't think that's ever the case. Forecasting uncertainty being too large does assist decision making by telling the decision makers that the future is very uncertain and they should be planning for lots of different possible outcomes and not assuming just one outcome or another. And one of the problems we have in providing forecasts to decision makers is getting them to not focus in on the most likely outcome, but to actually take into account the range of possibilities and to understand that futures are uncertain, that they need to plan for that uncertainty. Okay, let me finish there. My time's up. If you want these slides, they're available on my website at robjhyndman.com/uncertainfutures. Other papers and things you can get from my website. You can contact me on Twitter or on my email address, and there's my GitHub handle for all my papers and packages. Thank you. We'll now go to questions.
Okay, thanks very much, Rob. I can give you a round of applause at least. And yeah, we have lots of questions, so maybe we should just jump in. So the first is, are you also forecasting vaccination rates? And if you were, what kind of factors would you allow for?
So actually in the meeting we had this morning with the COVID forecasting panel, for the very first time, we started talking about forecasting vaccination rates and how to do that. We haven't yet done it. So, I can't say what we're doing because we haven't done it, but you would certainly want to take into account the current rates, but you would also be taking into account surveys on vaccination hesitancy, which would allow for population sentiment. And obviously there's some parts of the population that are extremely hesitant and probably unlikely to get vaccinated. You might also take into account incentives, but we haven't done any of that work yet.
Okay, next question. Nicholas Nassim Taleb takes a dim view of forecasting. Where do you think he's right and where do you think he's wrong, misguided / overreacting? Yeah,
so I know Nicholas, and while he is quite critical of some forecasting, he also does forecasting himself. And publishes papers in the International Journal of Forecasting. So he doesn't dismiss the entire field. His chief criticism is around the assumptions that often get made in models, particularly in finance. And one assumption in particular, which is around Gaussianity or normality, assuming that some of the things being forecast have a normal distribution, which is doesn't tend to happen. The other assumption he really doesn't like is that people don't allow for what he calls black swans, which is things that could occur in the future that have never occurred in the past, or you've never seen them in your historical data. He's of course right on both things. Like, we need to allow for other distributions, not make unreasonable assumptions, and you need to think about possible events that have not been seen in your historical data. But I think he's overreacting by dismissing, all of statistics in some of his papers and books, as if everybody does these things, and of course they don't. And but I think he's right in saying, get your assumptions more realistic and think about things that you've not seen in the historical data that could occur.
Okay, moving on. In the COVID application, why use linear pooling when you can give more weight to those models that turned out to give, say, a better one step ahead prediction? Yeah.
So we've looked pretty closely at that and tried to actually optimize the weights for different situation. So we've looked at optimizing weights within each state so that you would get some models would be more weighted more heavily in some states than others, or optimize them based on different horizons. But every time we've done it, the uncertainty in estimating those weights has also contributed to the uncertainty in the forecast. And we've felt that it was not improving it enough to deviate from the simpler assumption of equal weights. It's sort of an open question about whether you can do that estimation of the weights effectively without also introducing another source of uncertainty that you have to take into account in the models. Because just because your weights did well, if you estimate weights historically and they've done well on the historical forecast, doesn't mean they're going to do well on the future forecasts. So you have to allow for that estimation uncertainty as well. And when we do that, it doesn't really seem to help much. So we've just stuck for the moment with equal weights. But it is a question that researchers, not just us, but in other groups have looked at and are looking at.
Okay, a question about climate change now. When you consider forecasting things like electricity usage and water usage, etc., how can you take into account the potential effects of climate change? Have you thought about that?
Yeah, it's a really tricky problem. The only time I've had to do that was with long-term forecasting of temperatures, which we needed because we were putting them into our electricity demand model. We actually weren't so much forecasting temperatures as simulating possible future temperatures, but our simulations of future temperatures needed to allow for climate change when we're simulating them in 10 or 20 years' time. And all we did was look at climate reports from organisations like the IPCC and CSIRO and tried to adjust our simulations to allow for increased mean temperature and increased variations in temperature. But it was pretty crude. And I think it's a difficult question because, of course, we don't know what's going to happen with climate change. That is itself an uncertain forecast. We do know that it's going to increase. Temperatures will continue to increase. It's more around the uncertainty of those forecasts is hard to estimate, and the uncertainty of the effect of that on other things is hard to estimate. So yeah, I have some experience, but at the moment we're just doing relatively simple things when we try to take that into account.
So next question. I'm assuming, well, these questions keep jumping around, sorry. I'm assuming there are different measures of performance for probabilistic forecasts. What justifies the use of CRPS in particular?
Yeah, so probabilistic forecasting needs some kind of scoring method to estimate it, and it needs to have certain properties. So one of the properties you want is what's called proper scoring, which means that if it's minimized, then you've got the answer right. So the truth should give you the smallest CRPS, because we don't know the truth. We don't know what that distribution is. We're trying to estimate it. But that's one of the properties. And so that limits what probabilistic evaluation tools you want to use. And there's 3 or 4 that are relatively widely used. The other one, apart from CRPS, which gets the most use, is called log scoring, which is also relatively easy to use if you have the density of the forecast distribution. We actually don't have the density. We'd have to estimate it. We have, because we're doing this with simulation, it's much easier to work with CRPS than to work with the log scores, because we don't have to then worry about estimating densities of things. The other advantage of CRPS is that it makes it easier to focus on certain quantiles if we want to. If we said, well, let's see how good our models are at estimating the upper tail of the distribution and we don't care about other bits, it's very easy to adjust CRPS for that. But yeah, there's other choices we could have made. I don't think it would make very much difference in terms of which model is the best model.
So in the case of COVID forecasts, how would you incorporate things like quarantine leaks?
Yeah, so quarantine leaks affect the transmission potential. So when you'll see in my forecast, when we had long periods of 0 cases, our models were still allowing for the disease to take off again, and that's called seeding, where we have new seeds occurring in the transmission. So some of the models will put that in explicitly to say, well, even though there's no cases in the community, we will allow a certain amount of seeding to occur through quarantine leaks or through people coming from interstate who are unknowingly COVID positive. So yeah, we just put it directly into the model like that. And if quarantine leakage became much more widespread, then that particular component of the model would just increase.
So next question, can you give us an idea of how long it took to develop the models in these case studies?
Yeah, so in some ways, I've sort of presented it a little bit more simplistically than what actually happened, because often there was other case studies and papers that got written and so on. So in the case of the ETS models, I had already used a version of that before I did the PBS modeling, but I hadn't fully thought through the theory. So we did it much more systematically for the PBS modelings. And then there's about 10 papers that arose out of it and a whole book on the theory of these models. So just in terms of the PBS project, there was about 2 to 3 months of work, but in terms of the development of the models, it was several years of work. For the electricity demand stuff, from the time I started on it to when I finished, there was probably about 5 or 6 years we worked on these models, and I had a full-time postdoc. No, actually about 9 years, I had a full-time postdoc working on that stuff. COVID-19, easy to date, started thinking about this in around the 1st of March 2020. The tourism work was over a period of about 6 months. And that was, as I said, work with George Athanasopoulos largely, with some assistance from one of our excellent RAs, Mitya Harawald.
So there's one question that I can answer quickly. The question is, do we get the recording? And the answer is yes. You can look on the ACEMS website. The next question goes back to the PBS example. So when there is a known event, such as drugs entering or leaving the market, changes in policy and so on, can these be modeled?
Yeah, of course. You can build into your model interventions that can change things. So if you could have a model, for example, that says that in a certain class of drugs, then you've got a drug that's coming on the PBS, and we do a judgmental adjustment to our forecast based on what the uptake we think is going to be of that new drug. If a drug's coming off the PBS, then you could have if you know the sales of that particular drug, then you can easily use the data then to adjust your forecasts. So there is scope for doing that. Because there are thousands of products and a lack of personnel within the particular government department that was capable of doing this modelling, they opted for something more automatic than that, even though it would be possible to do that type of thing. So the models we produced were actually entirely automated without any kind of interventions. There was probably some later judgmental adjustments to what they used in the budget, but I wasn't involved in that process.
Do you have any insight into why different COVID models work better in different states?
Yeah, that's a great question, and I don't actually. I can only assume that some of the assumptions that we use in these different models are more relevant in some states than others. So the models are quite different. There's the SEIR models groups in the population, and it uses differential equations to describe how the rate of flow from one group to another. So the susceptible group and the exposed group and the infected group and the recovered group. And there's actually 2 in exposed groups with different conditions and 2 infected groups. So there's certain assumptions you make about mixing of people and how those groups interact. And I can only assume that maybe those assumptions are more, hold more closely for some states than others. But we're not actually sure why some of these models work better sometimes and not other times. That's one of the reasons we use an ensemble, is because we don't actually believe any of the models to be true, but we think they're all approximations to reality.
So next question, how do you go about explaining forecasts to decision makers, given that they're usually busy and might not understand what a confidence interval is and won't be happy if they're wrong?
So depends on the level of sophistication of the people I'm talking to. In some examples, particularly in the COVID stuff, we're talking to the AHPPC, which is a lot of highly trained scientific people. The chief health officers and the chief medical officer have all been, all extremely highly trained scientists and are quite capable of understanding probabilistic language. They're not necessarily used to it, but they quickly got up to speed with it. With the PBS, it was much more challenging because they were not even interested in seeing prediction intervals, even though I wanted them to look at them. They only wanted the numbers, the mean, actually. They only wanted a single number for each of these series, whereas I wanted them to think about the uncertainty associated with them, so that when they talk about the budget, you want to make sure you've put enough in the budget to cope with some of the uncertainty, not just the average. I don't think they ever got their heads around that. So it depends a lot on the complexity of that and the sophistication and the training of the people you're talking to. Mostly though, I've had pretty good success, largely through doing graphs like I was showing at the start here. The one where I showed a whole series of futures. I found these graphs actually to be really quite helpful in demonstrating the uncertainty and getting people to think about what it is when we give them a number like this blue line, what it is that means. So graphically, you don't have to do equations or talk very much about probabilities for them to get their head around it when you show them that.
So outside of natural disasters and the pandemic, what's the most unprecedented event that's impacted one of your forecasts?
Oh, that's a good question. I mean, obviously the pandemic is the most extreme event that I've had to deal with. Maybe some of the PBS stuff where you've had a huge drug suddenly come on the market that we were unaware of. So I remember there was an anti-smoking drug came on in 2001, which just had this huge impact on the costs of that particular drug category, and having to allow for that was problematic. So big events like that, but most of the work I've done has been sort of retail forecasting or demand forecasting or population forecasting, and then you don't sort of see such huge impacts that blow everything out of the water. It's much more subtle.
How have developments in machine learning produced anything of interest to the forecasting community?
So one of the most interesting things has been work on what's called global forecasting models, where you're fitting a model not just to one series, but to many series. And we actually did that in the COVID-19 case, but those ideas came from the machine learning community. Actually, Amazon was the first organization I know of to do that, whereas instead of forecasting individual products, they tried to build a deep learning neural network model for all of their products simultaneously, and use that for making predictions about future sales. And in about 2016, I was presenting some ideas to the Amazon Forecasting Research Group in Berlin, and we talked about this, and they were showing me how they were trying to build this deep learning neural network for the entire product base instead of doing one series at a time, which is what mostly we'd been doing up until then. So that's been quite influential, and a lot of people have started doing similar things since then, including my group. Okay,
I think we're starting to run out of time, but maybe I'll ask one or two more questions, and then we'll wrap up. So going back to your 4 forecastability factors, were they ranked in any particular order, or are they all equally important?
Let me go to them. I wasn't ranking them. The fact that they came out in this order was just the order I happened to type them in. Are they equally important? They're probably, no, I doubt that they're equally important. I just haven't thought about what order they should be thought of in. The future being similar to the past, I think, is probably the most important thing there, because if that's not true and you don't know how the future is going to be different from the past, then you're really screwed. You've got no idea what's going to go on. In various publications, I've listed 3, 4, and 5 of these factors. And if you search on the web, you'll find articles about Hyndman's 5 factors or things like that. I've reduced it to 4 because I decided the 2 of them were so closely related they could be considered the same thing. So this is the way I currently think of it. And probably number 3 is the most important, and possibly then number 4, but I haven't really thought enough about it to be definitive here.
Okay, maybe we'll make this the last question. When does the global AR model work better than the others? I think we're talking about COVID here, given that it's only taking the time series and not other factors like transmission and leakage, et cetera, into account.
So if you look at these graphs, it actually does reasonably well almost all the time. It never does badly. It's never the worst, and it always does reasonably well, and sometimes it's close to the best. The reason we think that's the case is that because we're using so much data from so many countries, then it sort of learns from all of that. It learns how the disease unfolds with different types of trajectories and sort of can adapt to it. Obviously, if there was major changes, if everyone got vaccinated or if the whole country went into lockdown suddenly, then our model's not going to deal with that because it's just taking historical data and projecting it forward. Whereas the other 2 models here are going to try to take into account disease transmission and disease dynamic behavior. But in a business as usual type approach, it does do remarkably well given how little information it knows about the Australian context.
Okay, so apologies if we didn't get to your question. There were a very large number of questions, but we're definitely run out of time. I'd like to thank Rob one more time for giving an excellent talk. And the next public lecture will be on Thursday, the 2nd of September at 12 o'clock. And Kerry Mangerson is going to be presenting the origami of data science. So hope to see you all then. Thanks again, Rob.